Okay, so in this example, we're going to evaluate a contour integral where the closed contour contains not one, but two, sorry, my circle is not so great, but two bad points of, two singular points of our function. So z squared plus 1 is 0 at 2 points, it's 0 at I, and it's 0 at negative I. All right, so let's go ahead and compute the integral over C, and C is this circle oriented always with the interior of the region it bounds on the left. So what we're gonna notice here is that if I were to put, let me say maybe in blue, a C1 here and a C2, we can imagine joining C1 and C2 with a path, say from A to B, and joining them, say C to D, and then joining, say E to F. Or actually, I don't need that one. Don't need that last one. So we could imagine integrating over C plus integrating from C to D plus integrating over C1 plus integrating from A to B plus integrating over C2 plus integrating from B to A, so that's the negative of integrating from A to B, plus, oh shoot, sorry, I messed this up slightly. What I want to do is I want to integrate over some of C1, so I'm going to not close it off. So I want to integrate over this part right here. So part of C1 plus integral over AB plus integral over all of C2 now. So we've gone all of C2 plus integrate from B to A, which is the negative of the integral from A to B, plus finish off C1. So I'm going to finish off C1 now, putting a circle integral there, plus integrating from D to C, or that's negative C to D. And that, the region that's bounded is the region outside of course, that's bounded between C and outside of C1 and C2, and there's no bad points in that area. So by the Cauchy-Gorsat theorem, this all adds up to 0, but some of this stuff cancels. All right, so we have that, but really, if we think about what we did, the integral over C1 and C2, it has to go this way. So that's the incorrect order, and since that's, or the orientation, so that's the incorrect orientation, really this integral over C1 is not integral over C1, it's the negative of the integral over C1. And really the integral over C2, sorry, that should be a contour here, is not the integral over C2, it's the negative of it. And so what we really have is something like this. And so in particular, this is going to tell us then that the integral over C dz over z squared plus 1 dz is the integral over C1 of dz over z squared plus 1 plus the integral over C2. And this is a generalization of the Cauchy-Gorsat theorem for what we call multiply connected domains. It's multiply connected because we have more than one hole necessarily. And so what this is saying is to integrate over more than one hole, you just integrate appropriate circle over each hole. Right? You want to make sure your circle doesn't contain both the points. So you isolate each hole and you do it separately. So let's do it. So let's also notice that 1 over z squared plus 1 with partial fractions becomes 1 over 2i times 1 over z minus I, and then minus 1 over 2i times 1 over z plus I. Okay, so that's the partial fractions decomposition. And so let's see. C1, the first guy, has information about when z is I, so this is related to C1, If we integrate the second one over C1, the singularity is not there. So this is going to be 0. So this is going to contribute to C1. This one's not going to contribute to C1. However, this has information about when Z is negative I, which C2 knows about. So this C2 will take care of. Well, it won't take care of, but it will contribute to the integral over C2. So the integral over C of dz over z squared plus 1 dz is going to be 1 over 2i, the integral over C1, this first part. And the second part of when we integrate over C1 is 0 because it's analytic inside of C1. And then we're going to get minus 1 over 2i. Well, for the integral over C2, the first part is now 0 because this function is analytic inside C2. So we just have to care about this second guy. And each one of these is 2 pi I. One over 2i, 2 pi I. And so we get pi minus pi, which happens to be 0 in this case. It's not always going to be 0, but it happened to be 0 in this case. And so this is how you deal with functions that have more than one singular point inside of the contour. You break them up, you sort of localize the integral. You only look at a small region of each of the singular points, and you try to understand your function there, and you integrate accordingly.